Okay, gonna make some more energy pie charts. Now, if you're a direction reader, which I suppose is a good thing, this might be a little bit confusing. Choose your system energy so the energies involved are internal to the system. We're not really going to do that because if you want the dissipated energy to be in your system, you kind of have to include a lot of things that you might not otherwise include. For example, if you've got like something skidding along the ground, it's got some kinetic energy, and then it stops here. It didn't change height, so this must all be E dis. For that to be like in the system, you have to include like the floor and the air around that might have caused some air resistance and whatever. So we're just really not going to fuss too much about that, or at all. Just making energy pies just like before. So here, restrict your analysis to the ball being in the air before it hits the ground. So I'm not worried about when it hits the ground here. So this is a real classic example that we need to understand. Here, before the ball starts moving, it's all EG. And here, when it's part way down, it's going to be part EG, and now it's moving, so part EK. And then at the bottom, this is the zero height, so this is going to be all EK. I'm going to say that's like right when it gets to the floor, so it hasn't actually hit the floor and slowed down or stopped yet. So that's why I can get away with saying it's all EK right when it gets there. Okay. Wind-up toy is wound up, then walks across the table and comes to a stop. So here's our little bunny toy again. So no EG because it's all at the same height, so I don't need to worry about that. EK, I've got a bunch, a little bit, and then nothing. So how about if I do this? Again, yours don't have to be exactly the same as mine. Just got to get the getting bigger and getting smaller, right? So that's what I'm going to do there. And then this is a wind-up toy. So at the beginning here, we would never include E dis in our very first pie because things haven't started to happen yet. So this must be EE. And then the amount of elastic energy cannot increase, right? The little spring is going to wind out. So maybe it went from like EE to EE to no EE there because it's the spring has wound out. So what's the rest of it? Well, that must be the energy dissipating. And it makes sense that this last one would be all E dis because it's just sitting there, the spring is wound out, and it's not moving. All right. So these, I'm going to take this right here at positions A and E. That's where the height is 0. So those will be the places where there's no gravitational potential energy. Okay. Those are supposed to all be the same size. They look like they're kind of getting smaller. That's not on purpose. So here, no gravitational potential energy, but the ball has been thrown up in the air, so it's got to have a bunch of kinetic energy. Velocity vectors beside each corresponding baseball in the drawing. Okay, that seems like a good idea. So it would be slower here, and then 0 here. I'm assuming this is going straight up and then coming back down. And then here, downward velocity, and when it gets here, same as in number 1, right when it gets to the ground, not after it hit the ground. Okay, so for kinetic energy, at the bottom it has all EK. And I'm going to ignore air resistance, so I'm not going to put dissipated energy in these. If you decided to put dissipated energy, a slice that's getting like bigger through B, C, D, E, that's fine. You can do that. Probably wouldn't be very much. And let's see here. I'm closer to the top here than I am here, so I just want to make sure I respect that. The slice of EK here at B At D, it's going to have a bigger one, like maybe half, I don't know. And then when it gets back to E, it's all EK again, right? It's all kinetic energy. It's back to the 0 height. And then everything else must be gravitational potential energy that it has because it's up here and then all the way up at the top where the velocity is 0 and then back down again. I think that looks good. Alright, an object rests on a coiled spring and then is launched upward. These little dots just represent the velocity. The fact that this is a dot means it's at rest. So it's pressing down on that spring. This right here is the lowest the rock ever gets, so I'm going to call that the 0 height. That is where the rock does not have any gravitational potential yet. So let's see, 1, 2, 3 to represent those 3 positions. So it's at the 0 height, it's not moving yet, so that means all of the energy must be in the spring at this point. Now, it has some velocity, and it also has some height. So some mix of kinetic and gravitational potential energy. The spring has done its thing, so the spring is out of the picture now. And then when it gets to the very top, it must be all EG, because it's about to start coming back down again. The velocity is 0 there at the top. Okay, piece of clay is dropped onto the floor, so it's falling, falling, and then splat. So let's see. Here it's, we'll call that the 0 height. This is maximum height. It's not moving yet, so that's all EG. Now here we're halfway down, so maybe it's about half and half EG and EK. And then splat, it hits the ground, so it has, it's at height 0, so no gravitational potential energy. It's not moving, so no kinetic energy, so it must all be dissipated. If you put elastic energy or something there, if this was a very bouncy ball, then maybe it would compress and then boing, back up again. But that is not the case here. It's a piece of clay. All right. Ball rolls to a stop on the floor. So at the start, it's rolling, has kinetic energy. This is all happening on the same level, so I don't need to use gravitational potential energy. And there's no elastic involved. And I'm going to, I guess we can't ignore dissipated energy. So at the start here, it's all kinetic. And then after a while, maybe it's like kinetic and E dis. And then finally, it's stopped. It's all dissipated. How about a truck being driven down the street? Looks like by the arrows, it's going at a constant velocity. So I'm going to go ahead and put that in first. That it's going at a constant velocity, so there's a bunch of kinetic energy. And where's the energy coming from? Well, start up in the gas tank, right? So let's say that we're never going to include, you could call this E-gas or E-chem or something like that. It's chemical energy. It's not a kind we're going to use too much in this class. We never start the first pi with dissipated energy in it, right? But as you drive down the street, definitely in the form of noise and heat, there's going to be energy dissipated from this truck. And then maybe a little bit more. So it's almost like, I mean, if these were like hours apart or something, it's almost like this line right here is like the gas gauge, right? Going down slowly until it's all E dis. Something like that. And last one. Super Ball is dropped and bounces up and down, and you can see that it keeps bouncing to lower and lower peaks. Where does the energy go? Well, it's going to be dissipated when it's dissipated in the form of it takes energy to compress the ball, and the little bouncy noise it makes. That's also some dissipated energy. So A, B, C, D, E. At the very start, that would be all gravitational potential energy because velocity is 0 at these peak spots. We'll say this is the 0 height, where it has no gravitational potential energy. So here, that must be all Eg. Now when it gets to the ground, see how the ball's squished down like that? There's some energy that's actually stored in the ball that's going to boing when it returns to its regular shape. So here at the bottom, there's no Eg. There is elastic energy. And then some of the energy, maybe not that much, make that a little smaller, is dissipated. Now once energy is dissipated, it cannot ever come back or become something else because it was dissipated. So if this is my E dis here, then when this gets all the way up here and the velocity is 0 again, it's all Eg again, but not this, because once it's dissipated, it's gone. Also, it hasn't got any bigger because it lost it in the interaction with the floor. So you can see Eg, smaller amount of Eg, which translates to less height. Okay, and then comes back down to D. And at D, it's all squished up again. So there's elastic energy. But the E dis must be getting bigger because it doesn't go as high. So something like that. All right, we'll have more chances to practice making these pie charts. That is how the game works.